Very good afternoon, everyone. So, in lectures 5, we will continue our discussion on convex sets and organically develop convex functions, but different varieties of convex functions that too. Look at strict, strong convexity, um, um, as well as look at examples of convex functions, and then move on to calculus of convex functions. In fact, hopefully, if we get time, we'll also start building upon the first order properties of convex functions. I've not listed it here, but yeah, that's first order properties. Then move to subgradients and look at calculus of subgradients of convex functions. Um, and then we'll also look at smoothness properties, Lipschitz smoothness, and so on. Any questions on the uh, projects? I think Prateek could take them and then you could leave. Yeah. Did you already? Were there any questions for Prateek or the TS? I hope everyone has submitted the form. Right. So if there are no questions, maybe Prateek in the next 5 minutes you could. So recap that while discussing the properties of convex hulls, we left you with the homework problem, some contemplation on what constitutes a supporting hyperplane. And the supporting hyperplane is characteristic of convex sets, right? But the supporting hyperplane, as I hinted, emerges from a more fundamental property. What is that property? What is the supporting hyperplane property here? A theorem, a corollary of a derivative of a separating hyperplane theorem. If you have two convex sets, they're guaranteed to have a separating hyperplane. Okay. Now, in the worst case, when you consider a point to be a point on, say, the boundary of the convex set, then what should this separating hyperplane give you? A supporting hyperplane, right? The separating hyperplane need not be a strict separating hyperplane. Okay, so right, and the reason this convex hull inspired this discussion was because when you consider the original set here, right, somehow you can't find the supporting hyperplane at all points. Moment you create the hull, you're basically now the hull is amounting to taking intersection of multiple half spaces. Do you see this? This hull, one way of defining the hull is what? Take all convex combinations, all points, right? So definition 1 of hull, convex hull basically, is convex combinations of all points, all pairs of points, right? Consider all the points. And you fill up the space basically, right? But there is a definition too. We'll try and present in a different color. And it's equivalent definition at a very intuitive level. And that definition is what? You consider a supporting hyperplane at each of these points based on which you create the hull. Let's say a supporting hyperplane here. Supporting hyperplane. Right? And consider the intersection of all the half spaces above these supporting hyperplanes. Right? intersection of half spaces defined by all supporting hyperplanes. So you take this one, right? That's also a hull. You see? So this is your first glimpse of what we call the duality. There are two different descriptions, two equivalent descriptions of the convex hull. One by construction, by constructing all the convex combinations. The other is by exclusion. I say, well, the intersection also means basically the other side, right? So supporting hyperplane was saying, well, there's a space I exclude from the set. The space that gets included, the intersection of all of these gives you the convex hull again. So this is basically a dual perspective, duality. Duality perspective. Yeah, we're very saddened by the loss of our very dear colleague, senior colleague, Professor Ajit Diwan. Very, very shocking. I mean, he's a person who excelled at, many of the the algebraic geometric perspectives associated, right? It's a big loss. When I was a BTech student here, he taught me. So, yeah, I don't know what to say. So, so the separating hyperplane is a more generic property, separating hyperplane theorem, and I had left you with a couple of homeworks. One was, of course, this contemplating on the supporting hyperplane theorem, how it results from separating hyperplane theorem, its connection with convex hulls. But I also left you with a couple more homeworks, which was how do you show that convex hull is always convex, right? So you need to verify that if you take convex combination of all points, that gives you the convex hull is indeed going to give you a convex set. So just concluding this discussion on separating hyperplane, I'd also left an optional reading, which is, and in fact, on Moodle, I do present a lot of optional reading. I hope you've been seeing Moodle. There's a lot of optional reading in case you're more curious. So there you can read more about the strict separating hyperplane, strict separation. But it suffices to say that if the boundary of the set that you're trying to separate from another set is not part of the set, right? Which means its set is open. Then strict separation becomes slightly easier. Slightly more nuanced. The discussion on strict separation becomes more nuanced. And I give you an example, right? If I'm looking at x greater than 0 and x equal to 0, right? Is there a strict separation? Is a strict separation possible? No, right? So even though the sets are disjoint, but x equal to 0 and x greater than equal to 0 are not disjoint. But x greater than 0 and x equal to 0 are disjoint. These are disjoint. So they are deceptively disjoint. Right? I said deceptively because no strict separation. Okay. So notwithstanding the strict separation use case, we can prove the supporting hyperplane theorem from the separating hyperplane theorem. Right, the supporting hyperplane at a boundary point x naught is such that while the equation satisfies x naught, for any other point x and c, A transpose x is less than or equal to A transpose x naught. So that this proves, this can be proved, sorry, by considering x naught to be separated from the set itself, right? So separating hyperplane theorem results by considering the extreme case. Supporting hyperplane at x naught in C is a separating hyperplane between x naught and C. Is this a correct statement? Or should it be the interior of C? Do you need it to be interior of C? I hope you have done your homework. Do you need it to be interior of C? Because see, all we are expecting in separating hyperplane is a greater than equal to less than equal to, right? Go back to this, right? A transpose x greater less than equal to B or A transpose x greater than equal to B for C and D respectively. You see this? So there's no strict separation, right? Inequality can exist. So can't we have separating hyperplane between x naught and C to be the supporting hyperplane at x naught? The only catch is x naught itself may not be in C because C may be an open set, right? So what will you have to do? So you'll have to make a small adjustment here. X naught could be in C or boundary of C, right? Okay, so give some thought to it. There's only a small adjustment you need to make here. Okay, so since this is not going to be a course on convex analysis, I won't be delving further into it. We'll move on. So the Euclidean ball is another very classic example. There's a radius r. Now, interestingly, when we say radius r, basically we assume that there is actually no skew at all. But if you do bring in some skew here, and the skew specifically in the form of an ellipsoid, what would you do? You would actually have x minus c. Earlier, this was a dot product between x minus c and x minus c. But now this dot product is being rotated and scaled. Is basically dot product is between a scaled and rotated version of x minus c. That gives you something called the ellipsoid. Okay. So, and a Euclidean ball and ellipsoid are very related. The relation is as follows. So, you can define an ellipsoid in two equivalent ways. One is, as I said, by bringing in some scale and rotation. X minus c transpose P inverse x minus c. The other way of viewing it is as follows. Instead of bringing rotation on the dot product space, basically it's a matrix induced dot product. We'll see a lot more matrix induced norms, matrix induced dot products. But there's another representation, which is you basically translate xc, the center, with a vector u, but this vector u itself can be rotated and scaled by matrix A, right? So one is to do this adjustment with the dot product between x minus c and x minus c, and the other is do this adjustment at the level of the radius, I mean the vector u itself, right? xc plus au. Now, if A is identity, you would get again a Euclidean ball. Else, you'd get an ellipsoid. There's of course a condition. A must be square and non-singular. Why is this condition required? A must be square. Why is square required? Why is A required to be non-singular? Non-singular, huh? Okay, square for dimension preservation. Yeah. This is syntactic correctness. And non-singular? Non-singular means inverse A. Is it could just collapse along some non-trivial u? See, what does it mean to say is non-singular? There's a non-trivial u, which means u is different from 0, for which AC may just become 0, and it collapses to the center. That you don't want, right? So very intuitive conditions. Yeah. Is that not the reason you are saying? I mean, norm of u less than equal to 1 is the same as saying norm of norm of x minus xc less than equal to r. I mean, there has to be some constant here, some bound here. Or whether you absorb that bound within A and make this r, or whether make it 1 and then absorb the scaling factor within A. That's up to you. So we can actually change it. We can call it some r here, and just A itself can be rescaled, right? But the more important point is A being square and non-singular. Very important to note this. Now it turns out that this gives us relation between A and P. Okay, so if you just substitute, right? A very simple substitution. What could you do? You would say x equals xc plus au, right? And with this, x minus xc transpose p inverse x minus xc would give you what? U transpose A transpose P inverse A. What? U. Right. So if A is P raised to half, then the two descriptions are equivalent. Okay. So this is what is happening. You had x minus xc less than equal to r. P is bringing a non-uniform scaling plus rotation. Therefore, you have a major axis and minor axis. The non-uniform scaling is making it. So you can take a scale by itself. That will still not give you a major and minor axis. And some notation also we have introduced here, Sn++. This is basically symmetric positive definite, which means all the eigenvalues are greater than 0. So it turns out that if A is square and non-singular, right, and if A is P raised to half, then P must be symmetric positive definite. Okay. And in general, Sn++ means a space, the set of all possible symmetric positive definite matrices, that is matrices with eigenvalues greater than 0. And the connection can be easily seen, right? If A is non-singular, then you can show that this quadratic term transpose, right? I mean, basically, X transpose Px will always be greater than 0. Vector transpose P into vector will always be greater than 0. That means all eigenvalues are greater than 0. Okay. Let's move on. I think we discussed the problem at length. Now there are a couple of other balls. While we have shown the ellipsoid, this is a special case of a Euclidean ball. There are many other balls. In fact, any norm ball gives you a convex set. What is a norm? A norm is basically one which has non-negativity. Norm x is greater than or equal to 0. Multiplication by scalar will give you what? Yes? The norm is going to be just multiplied by that scalar. And this is the third is called the triangle inequality. Norm of x plus x2 is less than or equal to norm of x1 plus norm of x. Sorry, norm of x1 plus x2 is less than or equal to norm of x1 plus norm of x2. Okay, so under this definition of norm, right, which generalizes the previous notion of norm, any norm ball at center x is a convex set. Right? So you could think of the some A induced norm A norm of x less than or equal to R, right? So question, when will this correspond to the ellipsoid? Well, sorry, this is A minus xc. Right, so I've just used A as a placeholder for the matrix induced norm. So what do you think? What should be the definition of this norm? And you need to verify that it's indeed a norm. Right now we are making a general claim. Any norm ball is a convex set, and we have stated that ellipsoid is a convex set. Now I want to show that ellipsoid views at a convex set is nothing but the matrix A induced norm ball claimed to be a convex set. So what is the matrix A induced norm ball? What is the matrix A induced norm? How would I define this? Yes?
X minus xc, A is half million. X minus.
So you would say raised to half, should I just put it as P? P raised to half is what you're saying? So should I use the A or the P from the previous slide? P? Or it will be P raised to half, which would turn out to be A. Think about it. So let's say this is defined to be x minus xc. Yes. What would I do here? No matter. Is this right? A to the power minus 2. A to the power minus 2 will give you P inverse. Right? So if you write it this way, it's P inverse. If you also want to consider the other case, you could just write it as, it's all about notation, right? X minus xc transpose P, in this case it will be P inverse. But there are many other such examples of norm balls. You know already one norm and infinity norm as examples. Can you show that this satisfies the triangle inequalities? The triangle inequality? The other two should be fairly simple. So should not be that difficult. The triangle inequality. Okay, so for any such norm, you get a convex set. Why? So by first principles, you can prove this. So I kind of outlined the proof here. So let's say this B is the ball. You take any 2 points, x1, x2, and then consider their convex combination. On the left hand side, step number 1 is the convex combination. Lambda x1 plus 1 minus lambda x2. The whole thing minus xc with the P norm. Now inside, I can expand, right? Because I'm still looking at the norm function applied to an argument, which is a convex combination, minus some C, xc. Now what I can do, this xc itself, I can expand it to lambda plus 1 minus lambda times xc, right? That's what I've done. This xc can be expanded as lambda xc plus 1 minus lambda xc. In the next step, I distribute the xc. You can see there's color coding. The parts in green I combine together. Lambda x1 plus 1 minus lambda xc, that is combined into the pink part. The green are combined into the pink part. Similarly, the yellow 1 minus lambda x2 plus 1 minus minus 1 minus lambda xc. The yellow parts are combined into this gray part 1 minus lambda x2 minus xc. Then the rest is simple, right? I'll do the following. I'll basically apply the triangle inequality. This entire expression is less than equal to this entire expression, the norm of the pink plus the gray is less than equal to the norm of the pink plus the norm of the gray, right? By triangle inequality. 3. And when I consider the norm of the pink part, I can again apply alpha x norm is absolute value of alpha into norm of x. That's what I've done here. Lambda into x1 minus xc norm. Likewise, the second part is, the gray part is also expanded as 1 minus lambda x2 minus xc, of course, with an inequality. Now, x2 minus x1 minus xc is less than equal to r, x2 minus xc is less than equal to r. So the right hand side is just becoming r. This is clear? So this is what we need to prove something by first principles. So all I've done is basically this pink part is the P and the gray part is a Q. And I've used that norm of the pink part plus the gray part is less than equal to the norm of the pink plus norm of the gray. This is the only critical step. And rest is to come to that inequality, help arrive that inequality. Okay. So think about it. How do I mean, can I just slap the Bittix induced norm therein and show that, I mean, this so-called norm is indeed a norm. So think about it. We'll not take this further in the class. Okay, so what next? Well, so ellipsoid is indeed a form of such norm. The definition we have adapted here is P norm or P induced norm for X is X transpose PX square, right? So I have taken the square. Oh, by the way, that is a mistake I made. I have forgotten to put a square root here. Okay, so it should have been a square root. By the way, I put that again. Okay, so I have actually used. Okay, so I have basically assumed this is P inverse here. And the slide it's all notation, as I said. So you can, in the slide, I've assumed that this P sitting here is a P inverse of what I wrote on the board. So under P inverse, X minus XT norm is X minus XT transpose P inverse X minus X. Okay, so with that, yeah, so this is just a solution to the problem. How every norm is a convex function, and how ellipsoid is a convex set with the two equivalent forms, what is the connection between the two, and so on, right? Now we move on to convex functions. So enough of convex sets. So convex function, a cup-shaped function, as you would always visualize, is a function such that it is always below the line segment joining any 2 points. Very, very intuitive definition. And that's where the connection with sets comes in, right? In sets, convex sets, what we said, 2 points, the line segment, joining them will lie inside. Now we are saying the curve, the graph should lie below. So in some sense, we are hinting at the fact that the region below is a convex set. Okay, but we'll come to that later on. Is it necessary that the region below, if it's a convex set, right? Then the function is convex. So ask these questions. Yeah.
Region then we take 1 point to the left side of that curve and then 1 point right side and draw straight line.
This region is convex, right? So let's draw it on the board. Let's try and depict what you have to do. Yeah, so what is your proposal? Oh, you mean, no, I didn't mean this part. Okay. Good question. So now there are a bunch of sets we are hinting at. Very good point you made. His point is, we should think about this region. This region, which doesn't appear to be bounded above, this is what he's saying should be a convex set. Okay, but there's one more set we can think of. This is one set. It's called the epigraph. Not epigraph. Yeah, I mean, this is an epigraph. I'm sorry, this is an epigraph. It's called the epigraph. Okay, but there is one more set. The set of all points that lie below a function value. So the set of all points for which the function lies below a particular value. So this is epigraph. Epigraph is nothing but x comma alpha such that fx is less than equal to alpha. We'll come to this later, okay? Don't have to write it now. I mean, not necessary. Right? So this is epigraph is in one dimensional higher than the original space. So if the function was defined on x in R2, right? This epigraph is in R3. The epigraph is in R3. On the other hand, consider another set X such that fx is less than equal to alpha, and let's call this set L alpha. This set is in R2. All the x for which fx is less than equal to alpha. What does that look like here? Let's take the same example. All the x, that will be what? This is what I meant. Okay, so I was basically saying take the regions below and project them into R2. Okay. So I'm going to post this teaser question to all of you. What is the connection between these two sets, which appear to be convex for a convex function, and the function itself being convex? In the sense, if LF alpha, which is the epigraph, so if the sublevel set, this is called the sublevel set. So if the sublevel set of a convex function, is it supposed to be convex? If the sublevel set is convex, does it mean that the whole original function is convex? Is the epigraph of a convex function always convex? If the epigraph is convex, does it imply that the function f must be convex? So these 4 questions, okay, leave you with these 4 questions. And we'll revisit these questions as we proceed. Four questions. FPF implies convex. Convexity. Convexity, does it imply FPF is convex? Similarly, L alpha F, does it imply convexity of F? Okay. And convexity of F, does it imply L alpha F is convex? So 4 questions.
Here for convexity.
Convexity of FPF. Yeah, I'm just keeping it very big. If a convex FPF, does it imply that? Does it imply convexity of F? Okay, 4 questions. Just keep them in mind. We'll revisit a little later. Don't have to answer now. Okay. I try and answer these questions. Okay, so I've just depicted all of this. Now, important thing is that domain F must be a convex set. So domain on which it's defined. So geometrically, basically this means that the line segment between x fx and y fy lies above the graph of F. This, right? This line segment should lie above the graph. So there are 2 sets which I had shown on the board and I've depicted them again. Same question I'm posting to all of you. What is the relationship between the green set? What is the green set? The green set is the second, in this case, the second set, L alpha F. So I'll just change this is second interest. I had shown, I had to show it. Second interesting set and the first interesting set shown on the board. So second interesting set L alpha F is x such that f of x is less than or equal to z for some fixed z. So L, instead of calling it L alpha, call it LZ. Okay. And the second set is, or the first set, which I've shown there, is x comma z such that f of x is less than or equal to z. That is the blue part above. You understand the green and the blue parts? Okay, so this is green on the board. This part is in green. What I showed as blue on the board is green there. And what I shown at white on the board is blue. on the screen. Okay. Now we come to another interesting class of functions called strongly convex functions. And we'll try connecting all these definitions to the different notions of sets we have seen. So what is a strongly convex function? Basically, if I subtract a quadratic component from the function and find that the new function is still convex, the function is like strongly convex, right? So that's one definition. Gx equals fx minus, now in that case, mu by 2 is a convexity, strong convexity factor. So if this is convex, then we say fx is strongly convex. I mean, this is a definition, so you can say there's a definition. Now there are other equivalent definitions as well. Again, go back to this board, the epigraph and the so-called sublevel set, right? These two pictures. Think of what would happen to those sets. We are not going to discuss this. Would there be any strong implication? Is there an equivalent notion of strong epigraph or a strong sublevel set? Think about it. But let's go back to the strong convexity parameter called mu. Right? So the more the value of mu, I think that means larger is the quadratic component I can subtract from the function and still ensure that the function is convex. So mu is a convexity fact, a strong convexity factor, and it basically shows that there is a quadratic lower bound on the growth of the function. The growth part will come when we talk about first order properties of convexity. You'll see this growth coming up more explicitly there. Now there is another notion of convexity which is called strict convexity. Strict convexity basically means that, I think I showed in the previous slide, if f of theta x1 plus 1 minus theta x2, right, which is the function at the line segment joining 2 points x1 and x2. We know that this is greater than equal to, but if I make this greater than f of theta x1 plus 1 minus theta x2 is greater than f of theta times f of x1 plus 1 minus theta times f of x2, then I say that the function is strictly convex. Okay. I think I presented that definition in the previous slide. Maybe, yeah, here I have presented it. I forgot to mention this. F is strictly convex if for all points in the domain, f of lambda x plus 1 minus lambda y. What did I do? Sorry, I'm sorry. The point on the line segment is higher. This point is higher. So it turns out that if a function is strongly convex, then it must be strictly convex. How do you prove that? Right? Strong convexity implies strict convexity. Some other interesting properties also I highlight here. So to show that one implies two, you will need to write strong convexity slightly differently as well. So please do that as a homework exercise. Okay. So I've left a couple of homeworks here. Okay. So first of all, as a hint, I've said homework 1 is derive the term T. Okay. So this is another equivalent definition. T such that f of theta x1 plus 1 minus theta x2 plus T is less than equal to theta f of x1 plus 1 minus theta f of x2. Okay. So this is blue, not blue is not visible, right? I'll write it in a red, not pink. So what I'm asking you to do is derive T such that f of theta x1 plus 1 minus theta of x2, the same term which I wrote for convexity and strict convexity, this augmented by this term T will still be less than equal to the convex combination of the function values theta f of x1 plus 1 minus theta f of x2. So this is a homework problem for you. Okay. And you have to take these homework problems seriously. As I said, you need to spend some time writing things down. Very, very straightforward. Okay. So now it's perfectly okay that this T is not something fixed. T may be a function of the theta, which is okay. But the T cannot be a function of, I mean, it has to kind of depend on, sorry? It could also depend on x1, x2. Yes. Now, should it depend on theta? That's the question. Sorry. Should it depend on theta? It can depend on x1, x2. Should it depend on theta? Can it depend on theta? So try and come up with this form, right? The hint is that it'll turn out that when x1 equals x2, this term will vanish, the T will vanish. Okay, so otherwise, when x1 is not equal to x2, this T will become positive. And as a result, this inequality will be a strict inequality, right? So this is strong convexity. This implies strict convexity. And why does it imply strict convexity? Since T will be greater than 0 unless x1 equals x2. Okay, so this is the key point. So that's homework 1. Is this clear? Now using the same hint, basically using the same definition, the T component derived, you can show that if a function f is strictly convex and g is just convex, then if you add them together, you'll still get strong convexity, which is very nice. So strong convexity, you just need to introduce once, right? And we'll see that strong convexity, the regularizer brings strong convexity. So moment you get in strong convexity, even through one term, it remains in the additive form. That's an advantage. Okay, also strong convexity doesn't imply that the function is differentiable, by the way. Okay. So strong convexity is not just adding second order properties to the function. It's still, you can still have strong convexity for a non-differentiable function. Okay. Any questions? So we have some 3 homeworks on this, right? Slide, all connected to what I wrote on the board. Let's move on. Okay, so these are examples of convex functions. The simplest is, of course, A transpose X, linear functions. Affine functions are another example. exponential function is a convex function. How do you show that the exponential function is a convex function? So one is to, of course, try and do the first principles. Can you use the Taylor series expansion to show this from first principles? Think about it. We'll find easier ways to do it. We'll derive more properties and do it. Every norm is convex. This should be easier. The fact that every norm is convex is the easiest to prove. And in some sense, we have done the proof today. Yes, triangle inequality. The proof lies hidden in the proof that we had for proving that norm ball is a convex set. Basically, you'll have the same set of inequalities. Okay. So every norm being convex is easy. Okay. So recap how we proved that norm balls are convex, right? We just did this. We took the P norm ball, expressed xc as lambda xc plus 1 minus lambda xc, invoke the triangle inequality as you pointed out, right? The pink and the gray parts are basically less than equal to the sum of the orange parts, right? Now each of this is the R. So the only difference here is, so here we had an xc. All we have to do is just show this. In fact, our proof is simpler here. We don't have an xc, right? We just have to show that theta x1 plus 1 minus theta x2, xc is set to 0, is less than equal to theta x1, theta norm of x1, sorry, plus 1 minus theta norm of x2. So you'll find that, I mean, you don't have to apply the R. Basically, just delete this part and you are pretty much there. Delete this part of the proof. Set xc to 0 and of course replace lambda with theta. You see, the proof is the same. Okay, so norm balls are, sorry, every norm is a convex function. Okay, so only difference is I'll just replace the lambdas with thetas, not a big deal. So if you want to set xc to 0 and okay. Okay, so we have proved that every norm is convex, and also using the triangle inequality like before, and the homogeneity of norm f of alpha x is alpha or absolute value of alpha times x, f of x, sorry. Okay, so this is easy. Now more properties. And now we're going to make a note of these properties. Okay, some of these are very recurring. So we'll use these properties. So whatever we have kind of proved, learned, we'll write down. Okay. So norm is convex. So second is, if you take two convex functions, scale them up by something non-negative, right, and add them, you'll still get convex function. So summation over I alpha I fi is convex if alpha i's are greater than or equal to 0 and fi's are convex. The third property is if f is convex and the argument of f you subject to some affine transformation, then you'll retain convexity. Okay. It's called affine transformation. Now look at this. This is interesting. So this f could be from Rm to R. Okay. F could be defined, let me get Rn. F could be defined from Rn to R. And A could be an M cross N matrix. So the function itself was originally defined in actually Rn. Let's change this. N cross M, sorry, N cross N. The function itself was defined in n-dimensional space. Now I take A, applied or as a for a affine transformation on X, which is in an m-dimensional space. So X is an m-dimensional space. So I have now created a convex function with arguments in Rm based on another convex function, based on a convex function which had arguments in Rn. Okay, so that is something interesting, which means you could have a function operating on scalars and suddenly you get a function operating on vectors, or vice versa, right? M and N can very much be one, or like M could be one, N could be one. So that is a point you should register. Suddenly you've got a lot of power with this one property.
Are there any restrictions?
For any choice of A. So yeah, I'm giving examples here, and we'll see how these are. I mean, this is the probably the most canonical. Fx is norm of Ax plus B, right? So norm applies on some vector space. Now X itself could be in some very different dimensional space, right? And it could be some very large dimensional space which I shrunk to a smaller dimensional space, take a norm there. The other example I've given here is log applied to an affine transformation. And sorry, negative of log. Okay, why is negative of log? Well, negative of log is convex. Okay, that is another. So we'll norm is convex. We'll just take some point number. So let's call this 0. Okay, point number 0 are just examples. Point number 1 is actual properties. exp minus log are convex, and we'll see why they are convex using more ammunition a little later. But for now, assume that these are simple functions. Now, for those who have done right in simple calculus, you would just take the derivative, right, and show that for a convex function, you would expect the derivative to be what? Non-negative. The derivative or the double derivative. So you would expect the derivative to keep increasing, right? So you can, or the double derivative, it's a derivative to be increasing or the double derivative to be non-negative. Okay. But we'll see that later on. So let's do one thing at a time. Now we come to some slightly more non-trivial properties. So all this is part of the so-called calculus. These properties are giving us what we call so starting point number 1, right? The point number 1 onwards is the calculus of convex functions. So point number 3 is about compositions. And you can show that certain compositions are convex given some properties of what you're composing. So what you're composing matters, right? So if f is convex, what you have done, f is h of g of x. So if g is convex, h is convex and non-decreasing. So look at this interesting keyword, right? And I'll try and be depicted here. So g must be convex. Argument inside it should be convex, and h, the argument outside, is convex and non-decreasing. Okay, so non-decreasing is important. I mean, increasing is of course sufficient condition. Non-decreasing is a necessary condition. Or if G, the inner argument, is concave, then you need H to compensate for a concave G by becoming non-increasing. So this is what it means, right? So if the inner argument, in plain words, composition of H with G, if the inner argument is convex, the outer argument is convex and non-decreasing, or the inner argument is concave and the outer argument is convex and non-increasing, compensating for the concavity of G, the outer argument should be non-increasing. Right? Some kind of effect, some cancellation of the concavity signal through a non-increasing nature. Then the composition is a convex function. Okay. So this is best pictorially depicted. Right? So G, f of, sorry, h of g of x A. Okay, you can register. I mean, you can use a color depiction in your notebook just to keep things easy for recall. Right? Now you can prove this from first principles. What is first principles going to do? You're going to basically write down all these convex combinations the way we did for norm. I'm not going to do that in the class. We don't have time to spend on that. But you can use this in terms of pairs of points. Okay, so you can also do that. Do the following using first order conditions later on. I will not do that now. That also is a way of doing it. If you consider derivatives, that's another way of showing. But I'll say first principles are fairly straightforward. The way we did for norm, just do it here. First principles are simple here. So M is basically the dimension. So I mean, basically, if the argument is one dimensional, you can easily show this. See, what I'm trying to say is we are coming up with an advanced version of this. We have not. We're going to have G convex in a vector valued set of arguments. Then we can have H convex in a vector valued set of arguments, and then G, you think of each point in the argument. So I was just trying to allude to that. It'll come. It will come soon. Okay. So you can show that exp of f of x is convex if f is convex. Why? Well, if f is convex, the inner argument is convex. exp, how is it? How is exp? Sorry? Convex and non-decreasing. This is the first case. F, the inner argument is convex, and exp is the outer argument, which is convex and non-decreasing. On the other hand, 1 by g of x, how does that fit into our scheme? Yes, 1 by g of x. Okay, the inner argument, well, gx, g is concave, right? G is concave, and 1 by x, which is what is h, is concave, right? So how does it fit here? Does it fit here at all? Sorry? Sorry? 1 by x is? So would we expect this to be G is, of course, G is positive. In fact, G is positive. So which of these two cases does it fall in? The second case, G is concave, H is convex and non-increasing. No, 1 by x, x is positive. This is G is, so the G, I mean, G is assumed to be positive. So I mean, I have a homework problem. What happens if G is allowed to be negative? Is that clear? Okay. So 1 by g of x is convex by virtue of the second property. That is B. Now we look at the slightly more complex case. What if the H is applied to a vector where each component of the vector is a scalar function, right? Is the output of a function gi. Now, can we just extend these two cases, A and B, with A becoming now the GIs, the individual GIs being convex, H is convex and non-decreasing in each argument. Okay, so EG is convex, GI instead of now G, GIs are convex, and H is convex and non-decreasing in each I, in each argument. Or if GIs are all concave and H is convex and non-increasing again in each argument. In each I.
These map from R into R.
Acha. G is mapping from
So that given an R.
GI is mapping from Rn to R. But the G itself is a vector of GIs. So this is a G, not GI. Clear? Okay, now we're looking at some interesting properties, interesting functions. These are somewhat non-trivial. Okay, what is the first function? It is log of the sum of the log of GIs. This is actually still okay. The first function is easy. Sum of log of GIs. Why will this be? Minus of this. Why will minus of this be convex? That's because minus of log is Minus of log is convex. If GIs are concave and positive, then minus of log is convex and non-increasing, right? Minus of log. Minus of log. I mean, here I've taken log. Log is concave. Okay, by the way. So I've made a leap here. A function is concave if it's negative is convex. Okay, so sorry. There's a little bit of leap I'm going to use off and on. A function is concave if it's negative is convex. So what have I done here? I basically, let's take an example of the second one. Minus of log, sorry. If GIs are concave and minus of log is convex and non-increasing. So you see, this is a case of B. This is clear? This is a case of P. The first one should be easy to show. Sorry. The second one is tricky, certainly tricky. And the second one is something you want to see all the time in ML. It's called the log of sum of exponents. How many of you have come across that while coding? Log sum exp, right? If you haven't come across, you need to code more, right? It's a reflection of the fact that you haven't coded much. So log sum x is going to come up every time you do some normalization. You take a maximum, a likelihood that you want to maximize. You need to do normalization. Because most of our functions have an exponentiated form, right? Exponentiated distribution. So how do you prove that this is convex? And this is actually, its convexity is very critical for ML. Do you think it fits into any of A or B? Log sum x, does it fit into the composition A or composition B? Okay. So I'll tell you that fitting into A or B is not going to be easy. It might be possible with a lot of hard work, but it's not something that you will be able to do immediately. Right, the hint is you'll have to do a little bit more work. I mean, in fact, you can prove it even without a composition property. The hint here is you should use another derived property called midpoint convexity. So I'm going to write that as another prop. It's such a silly small extension that I don't feel like wasting board space on it, but I will do that anyways. Maybe I'll use a very small piece of the board. It's called midpoint convexity. Okay, what is midpoint convexity? Just says theta, take theta to be half. Right? A function is convex if it is midpoint convex. If and only, which means R of x1 plus x2 divided by 2 is less than equal to half of, right? So, or G, I'll just use here F. F of x1 plus x2 divided by 2 less than equal to half f of x1 plus half f of x2. So if you have this property, then you can say the function is convex. Midpoint convexity implies convexity. See, midpoint convexity is a special case. But if you show that for half, you have shown it for all theta. Yeah. How does it imply? you have to, it's possible to show it by first principles again. You can show that any convex combination, let's say theta x1 plus 1 minus theta x2, can be written as, with some adjustments, the midpoint of some two other terms in terms of x1 and x2. Okay, so it's possible. It's not difficult. I mean, it is actually just say doing some linear. It's a translational relationship, right? And you're translating from theta to half, the way we did for ellipsoids. I mean, for us, the Euclidean ball stretched and somewhat non-uniformly scaled gave you an ellipsoid. So there's a little bit of non-uniform scaling going on here. Is this clear? If you got convinced with Euclidean ball to ellipsoid, this should not be very difficult. Okay. So can you show that midpoint convexity can give you convexity of log sum x? Okay, that's the question. So here is it. So using midpoint convexity, I prove that log of sum of exp is convex. So basically, I want to show that h of x1 plus x2 is less than or equal to half of h of x1 plus half of h of x2, right? And h is the outer function. In this case, log. Okay, I can do that, and that's not difficult. Log of sum of I exp x1 I by 2 plus x2 I by 2 is nothing but the sum over i's of exp I by exp I1 x1 I raised to half, the square root of exp x1 I into the square root of exp x2 I, right? The sum of exponential sum on the exponents becomes a product of the exponentiated terms, right? So I'm going to just denote this term. Okay, so this term is exp x1 I the whole raised to half as alpha I. Similarly, exp x2 I the whole raised to a half as beta I. Okay, that's what I've written here. Okay. With this simplification, so this is my LHS. My LHS is basically for log of the sum of the exps. On the right hand side, what do? I want to show that half of hx1 plus half of hx2, which is the right hand side, is greater than or equal to the left hand side. So I'm going to now expand the right hand side. Half of log of sum of exp x1 I plus half of log of summation over I of exp x2 I. So now if I expand, right, the sum over the i's of exp, the half times, there's a half here, half log, right? So this half will now become raised to, right? You'll raise the sum over I of exp x1 I, the whole thing raised to half. Similarly, sum over I exp x2 I, the whole thing raised to half. So log of sums has become, the sum of logs has become log of the product. That's point number one. And the scalar product with the log has gone into the exponent within the log. You understand these two things that have taken place? Okay, so theta log will become what? Theta log will become log of x raised to theta, and log of x1 plus log of x2 becomes log of x1, x2. That's all I've done. These two expressions have been used. Okay, so with all that working out, you can show that you'll get this green part. The left hand side will become log of summation of the alpha I into beta i's. The right hand side will become log of summation alpha I squares the whole raised to half into summation beta I squares the whole raised to half. And the interesting thing, I'm saying the log is, how is log? Log is a non-decreasing function. Log is not decreasing. It may be concave, but it's not decreasing. Now, if it's not decreasing, then if alpha I beta I can show to be less than equal to alpha I square summation raised to half into beta I square summation raised to half, then I can show this inequality. But the arguments have that inequality because of Cauchy-Schwarz inequality. You know Cauchy-Schwarz inequality. Basically, I've taken two vectors, alpha vector, beta vector, take the dot product, is less than equal to the norm of alpha and the norm of beta. That's Cauchy-Schwarz. So that's why midpoint convexity held. But there is a generalization of Cauchy-Schwarz which will help you generalize and show the convexity of, the concavity of log even beyond midpoint. So okay, so I'm going to leave you with a homework problem. I will look at this later on, but I want you to, I'll leave you with some questions. Okay, you need to think on whether which of these functions are convex. L1, L2 regularize logistic regression. L1, L2 regularize SVMs. L1, L2 regularize multi-class logistic regression. Least squares, L1, L2 regularized as well. Matrix completion, is that convex? And softmax contextual bandits, are they convex? Okay. So since it's a little fast paced, you'll need to now apply all our properties. There are some properties we have not covered, which is okay. We'll cover them. Only one property is left. But pretty much all the important properties are done. Log sum x is probably the most important property. So please, as your homework, also reflect on which of these are convex and why. And unless you write, you're going to have difficulty. So please make sure you have, you're maintaining good notes. Thank you. Yeah.